opportunity and online classification with partial feedback.
Thank you, Nicole. First of all, I want to start by thanking the organizers, Moni, Nicole, and Stephen. The talk is based on joint work with Katrina Leggett, Aaron Roth, Bo Wagner, and Stephen Wu. I would like to start with a very simple. This thing doesn't.
Turn it on.
Yeah.
There's a USB thing to plug into. Yeah, say that.
Okay. I'd like to start with a very simple online classification setting. So this guy is a weatherman here. And as a part of his job requirements, he's required to predict with good accuracy whether it's going to be sunny or rainy tomorrow. So he also has access to field measurements, so the temperature today or the wind and the humidity, and he has to make a prediction. The next day, he finds out if he got it right or made a mistake. And we don't want to make mistakes. The point is, regardless of the prediction made, you have two arrows here. This is because whether predicted sunny or rainy is going to find out whether the prediction was correct or not. So the feedback comes regardless of the prediction. Whereas the majority of settings where fairness is a primary concern are actually partial feedback and not full feedback. So if we're talking about lending, hiring, college admissions, recidivism prediction, online advertising, predictive policing, medical treatments, they all have one thing in common. This is we only observe feedback for one of the predictions. So for lending, we only observe feedback for the candidates we actually approve of a loan. For hiring, only once we hire have the ability to demonstrate that there will be good employees. And the same with college admissions and each of these settings. So let's just talk about this lending setting where you have a bank, and on each given day, an individual shows up. The bank sees the measurements of this individual, like the income, the age, or whatever measurements that might help him to make a decision. And the bank either approves or denies this individual of the loan. But here, we only have one arrow because we don't see feedback for people who are denied of a loan. So this is partial feedback. And the consequence is that decisions not only affect how accurate we are, but also the amount and type of data we collect. So the decisions we make along the way also affect our ability to learn what are the best policies in the later phases of the process. And the standard techniques on gathered data might lead, if we're not careful, to feedback loops and risk being highly unfair. So I'll give one example of that in the form of the PredPol system that is currently in use in about 60 police departments across the US. And one of the main concerns was that if you start with neighborhoods that have different crime rates, PredPol is going to suggest that you dispatch more troops to neighborhoods that start with a higher crime rate. And then as you do that, they're going to naturally detect more crimes. And then in the next stage, the loop is going to reinforce itself. So you have a self-fulfilling prophecy. And this is just an article from the news. Academics confirmed that major predictive policing algorithm is fundamentally flawed. And the model that they use in this algorithm, the core of it is based on earthquake prediction. So you have this model where it says, like, if you have an earthquake happening in some region, naturally you have a higher probability of this recurring or happening again. And this is what Christian Lom had to say about the PredPol study, 2016. The key point of the PredPol study is that virtually all predictive policing models use crime data from police departments. But police department data is not representative of all crimes committed. Police aren't notified about all crimes that happen. And they don't document all crimes they respond to. Police recorded data is a combination of policing strategy, police community relations, and criminality. If a police department has a history of over-policing some communities over others, predictive policing will merely reproduce these patterns in subsequent predictions. This is the exact concern here. So formally, our problem setting is online classification with one-sided feedback, not full feedback. So let's go back to the example of lending and this bank here. This bank has 3 possible loan policies, denoted here by blue, orange, and green. On every round, the bank has to commit to one of these lending policies. And let's say this round, the bank selects to commit to the blue policy. And then on each day, an individual shows up. And this individual is either approved or denied of a loan according to the policy the bank has committed to. So the bank the policy the bank has committed to is binding for any individual that might show up. And this is important. Next up, the prediction is made according to the individual and the policy. The individual is either approved or denied, and we see only feedback if the individual is actually approved of the loan. So a natural measure of how well the bank did at the end of this process, let's say that it runs for some number of days, the bank might ask, how well did I do compared to the best available policy? Let's say it runs for 5 days, and this is the sequence of selections made by the bank, and the best policy is the green one, and the bank might compare his performance to the performance that would have been achieved by the best one. So this is just the usual notion of regret. So this is H star here is the optimal policy, in our case the green policy, and this is just the loss, the expected loss over T rounds of this optimal policy. And what we have here is just subtracting the cost or the loss incurred by the bank by playing HT here is any of the policies that the bank played in the sequence, comparing to the loss that would have been achieved by just sticking to the green policy. So the talk is going to be, the outline is going to be the following. First, I'm going to talk about low regret with one-sided feedback. Next, I'm going to talk about the fairness definitions that we have and how we incorporate that. And then I'm going to combine the two, fairness and one-sided feedback. I'm going to suggest an algorithm and a lower bound, matching lower bound. So let's start with low regret with one-sided feedback. So as a warm-up question, can we even guarantee low regret despite only seeing one-sided feedback? So how can we expect to guarantee low regret if the learner can't even measure its own regret, right? If you make negative decisions, if you deny people of loans, you don't even get to see if this individual pays. So you don't have a good measure of your own regret. So looking at just like the very simple basic 0-1 loss, we can see that in the second row, individuals that are denied, we cannot observe what's in the second row here circled by red. So each individual that we deny of a loan, we actually don't observe that. So how do we go around this difficulty? We just add a vector of 1s to the second column of this matrix. And then what we get is that for the second row, we get constant payoff. So regardless of the decision that was made, and regardless of whether this individual repays or defaults, if this individual was denied, the payoff is going to always be 1. The loss is always B1. It's a constant loss. So what we actually get by that is that we can easily cast this problem from one-sided feedback to a contextual bandit problem. So remember, contextual bandits, we have a finite number of actions, in this case 2 actions, approve or deny of loans. And we have the context that in this case are individuals. And the policy class that we want to compare with is mappings between context and actions. And so in this case, we have the purple line here for people who are approved. And then for people we approve of a loan, we pay either 0 or 2 if this individual repays or defaults. And here in the gold line, this is the second action. People we deny, we constantly pay 1. So in this case, we don't really even observe this line. But since this line is constant, whenever we deny somebody of a loan, we know what's going to be the payoff. So we actually have this bandit setting where we observe any of the lines or each of the lines according to the prediction that we make. Why is this useful? Because we have good algorithms for contextual bandits. So we can, by casting this problem as a contextual bandit, we can use this algorithm. So, okay, so we did this transformation on the loss matrix. So one question is, why can we even do this transformation? Doesn't it affect the regret guarantees that we are going to get? So an important observation is that the loss matrix is regret preserving. So if we look at the transformed loss matrix, and we look at a stream of individuals over time, so the loss of any hypothesis here, the transformed loss, if we measure it, is just the original loss, which is the term here, under the original 0, 1 loss matrix, plus this additional term. And this additional term is just the number of red rounds here. So red rounds are individuals that default. So these are the bad candidates. So any round that a bad candidate shows up, regardless of the made decision, we pay 1 more because this is 2 and 1 instead of 1 and 0. So the takeaway is that for any hypothesis, regardless of the predictions made, we have just like an additional term that depends on the number of bad candidates showing up in the stream. So regret does not change if you compare 2 hypotheses, even after you do this transformation. As a conclusion, given a contextual bandit algorithm that guarantees some regret T, we can translate it to a one-sided feedback algorithm that guarantees twice the regret. And the 2 factor just comes from the rescaling of the loss matrix.
But this is only formality because this may not be the regret that you care about. You have constant regret for people you rejected, but maybe your real regret compared to what would have been the optimal option would have been different than this constant.
It's the same regret.
I'm not sure I get that. It's the same regret that you're measuring.
I assume 0 regret if you do original.
You have the same regret against the policy that you're measuring.
Because you assume 0 regret for everybody that you denied. But that's not the realistic situation.
No, it does not assume that. Just classification.
Okay, I'll take it.
Okay. It's the same regret that you're measuring against the policy. So.
I think he was like questioning the payoff matrix, that like the symmetry, right? That like if you reject someone, you should have given a loan.
You always pay. You always.
The question about the payoff matrix, which is the setup and not about the, okay.
Oh, yeah, but okay. So the bottom line is that you can get the same regret up to this constant factor here. Okay, the next question is, when we look at the setting that we have, now next, what about fairness? So we have this online setting with partial feedback, and on each day, the bank deploys a loan policy, here denoted by HT. A natural requirement would be that this loan policy that is binding for any individual that shows up would be a fair policy. So in order for talking about fairness, we have to first define the measure of fairness that we're working with. So first of all, just a technical note, we allow deploying a distribution over hypothesis and not just a single hypothesis. This will be helpful to get better trade-offs with accuracy and fairness. And the definition of fairness that we will use is a false positive rate or the false negative rate. Here is just like the usual definition, but we also have probability over the selected hypothesis from the distribution over hypothesis pi that we deploy at every round. And the second term is just the difference of the false positive rates of this policy on the 2 different groups in the population, denoted by 1 or minus 1. And the definition is that we say an algorithm is gamma fair if on every round the difference of the false positive rate of this policy that we deploy is smaller or equal to gamma. Good. Now, as a first example for that, let's say that we have a hypothesis class with 5 different hypotheses. These 2, pos and neg, are just for accepting everyone or denying everyone of a loan, just constant policies. they have zero false positive difference because you either accept everybody or deny everybody. And let's say that we have H1, H2, and H3. So the feasible regime is this blue shape here. And these are the trade-offs that you can get. But if you also want to be gamma fair, it's just this green area. And if you do not allow randomization, the best one that you can choose is actually H2 here. It gets you the best trade-off. But if you also allow to randomize over hypothesis, you can get to this optimal point. And an observation that is useful in our paper is that the optimal gamma fair policy is always of support sides at most 2. Here, a combination of H1 and H2.
So, sorry, when you define that false positive rate, is it can you go back one?
Yes.
Is it the rate you actually make the decisions, or the rate you kind of like intend to make them before?
The false positive rate is on the underlying distribution. So you want the policy that you deploy on each round to be.
I see. So you're not actually counting the number of decisions you make. Like if I'm about to flip a coin,
Okay.
then you're not counting how many times I actually denied somebody. You're just counting how what's the.
So it's defined over on expectation on the underlying distribution, not the realization.
But I guess those quantities will concentrate around each other.
Well, not earlier on, right? Okay, that's fine. I think
So going back here, the optimal point is this one.
sorry, Aaron, it's not, you only have one draw for each policy, so there's no concentration. If I understand correctly, you actually use each policy only once.
But each
Why would you use each policy?
Because
only one?
every round you're going to have a different policy, and you're going to keep updating your policy.
Yes.
So you're going to draw you can actually use each policy only once. So there's no concentration. You don't really have a concentration.
but each one guarantees individually that the difference in false positive rates is
So
close. You think of the random.
Yeah, so each policy that you use, you can use different policies, but each one has this guarantee on the underlying distribution.
So there's sort of a question over here. So if you're only getting one-sided feedback, can you measure the false positive rate?
Yeah, this is a good question.
I mean, you could measure the false discovery rate. But
Right. So this is a good question, and I'll address it in the following slides. Yes. All right. So the question that we ask is, what is the trade-off between fairness and regret in the partial feedback setting? More specifically, if we constrain our policy to be gamma fair on every round, what is the regret guarantee that we can give? So this is the third section, and here I'm going to talk about the algorithm that we propose for the fairness and one-sided feedback setting. So this is the main result of our paper, and the main result is that there exists an algorithm that runs in polynomial time, given access to an optimization oracle. I will talk about this in the following slide. Over H, and guarantees the two guarantees here, that the fairness on any given round is gamma plus t to the minus 1/4 fair on every round, where gamma is just any constant between 0 and 1. And the regret is roughly the order of root t log h to the best gamma fair policy in H. Okay.
So what is a round?
The round is, you have time steps of the algorithm.
What is t compared to a round? What
You
is
mean capital T? Capital T is a time horizon. This is the total number of rounds. So you run for capital T rounds.
You run for capital T rounds and you pay per round?
Yes, and the per round the per round fairness that you have, so scales like this with t to the minus 1/4. So think about like t as an order of 100,000 or 10,000.
Okay, so it's on average t to the minus 4 over the rounds.
What do you mean by on average?
Expectation.
This is what you get. So with high probability, the policy that we deploy on every round is going to give you this amount of fairness on the underlying distribution. Okay. Good. So I'll just mention briefly, so this is the mini-monster algorithm by Agrawal et al., an algorithm that we use as a building block for our algorithm for a fair one-sided feedback setting. This is an Oracle efficient algorithm. It also gives high probability guarantees for contextual bandits. But this algorithm has no fairness guarantees, so we want to also insert fairness guarantees to make sure that the policy we deploy on every round is fair. So the algorithm that we suggest is the following. Let's say that here we have the time scale. So first of all, for an order of root t log h rounds, the first arrivals are all labeled. We all predict them to be positive to observe the labels. So this is just the people that show up here. Then, so D sub E here is the empirical distribution of measurements and true labels of these individuals that show up here. And we use the empirical distribution to build H fair here, which is the policy class. So these are only policies, right? Probability distributions over hypotheses that are empirically gamma fair on the observed distribution, okay? And we instantiate the mini-monster algorithm according, so with this hypothesis class, with H fair. So mini-monster algorithm is going to always play a fair policy, and is going to guarantee us the regret guarantees that were in the former slide on these people. So one observation to make is that we don't really explicitly build this subset of the policy class. So this is where the optimization oracle that I mentioned earlier enters the picture. So here, mini-monster is an oracle efficient algorithm, and the oracle that we are going to construct is going to be a fair cost sensitive classification oracle. So I think Aaron mentioned this earlier, but cost sensitive classification problem is just you have a set of points, costs for predicting positive, negative, and you want to minimize the total cost, and it's equivalent to weighted binary classification. So what we use in the paper is we actually rely on having an access to this CSC oracle, and on top of that we build a fair cost-sensitive classification oracle. So the theorem is the following. Given nu here, which is the approximation concept, there exists an oracle efficient algorithm that calls the original oracle for at most 1 over the approximation term squared number of times, and outputs a gamma fair distribution such that the cost, so this is according to the randomness in the policy, so that the cost is the optimal cost plus some approximation term. And this, the proof of this is just adapted with from the Agrawal et al. This is a paper called The Reductions Approach to Fair Classification with some technical changes that I'll mention in the next slide. So the access here is just mini-monster, this contextual bandit algorithm has access to the H fair, to the class of fair policies on the empirical data through calls to the fair cost sensitive classification oracle. So it does it in an efficient way. So in the paper, we also adapt the cost sensitive classification oracle to the fair version. In the case where the fairness constraint is only defined on the subset of points considered in the cost objective. So going back to your question, we only use a subset because we can only measure the false positive rate on the first, on people who show up in the exploration phase, because we cannot measure the false positive rate on people in the second phase.
So if your definition of fairness was the false discovery rate, would that t to the minus a quarter term go away?
False, you mean?
I mean, that's the fraction of people who you did give the loan to who defaulted, for instance, or the fraction of people who you released who, wait, hold on.
You mean the false negative rate?
Same numerator, different denominator.
You mean the false negative rate?
Well, depending on which you call positive or negative, yeah.
So the answer is that the algorithm, so if we switch the definitions to false negative rate or statistical parity, the algorithm would just work the same. But for different definitions of fairness, this is something that is not yet guaranteed and we might want to explore as a next step. And the second difference, so the regret analysis for the fair version of the mini-monster algorithm, we also have to take into account an additional approximation error. So we have this approximation error because we construct the fair cost-sensitive classification oracle, and because we have a problem with false positive rate constraints, in order to maintain those constraints, we induce another approximation error for the objective. So we also have to take this into account when we analyze the regret of the mini-monster algorithm. So for those of you who might read the paper, this is in the analysis. Okay, next up, the lower bound. So the claim is the following. There exists a hypothesis class H such that any algorithm that is t to the minus alpha fair must have expected regret, which is the order of t to the 2 times alpha. So this is a matching lower bound to the upper bound that we just stated if you pick alpha to be 1 quarter. So any algorithm that is t to the minus 1 quarter fair, the regret scales as log t, as root t, sorry. And what's the idea of this lower bound? We define two similar distributions, D1 and D2, small scale divergence between the two. And until it's able to distinguish the two distributions, an algorithm has to act very conservatively. Otherwise, the algorithm risks being unfair. And by acting conservatively on the first rounds, on each of these rounds, the algorithm incurs high regret. So this is the construction. Let's say we have these two distributions, D1 and D2. And let's say these are the available hypotheses here. So this is predicting positive on everyone, predictive negative on everyone. We assume that the base rate is 1/2, so they're both on the same point here. And we have two other hypotheses. One of them is the optimal one, and the optimal hypothesis on the first distribution is this H2, completely fair. Whereas the other hypothesis, H1, is unfair because it falls outside the gamma fair regime, but it's 4 times gamma fair. So in order to find the best hypothesis, which is either H2 or H1 in this case, and since the algorithm is gamma fair on every round, so in the first case where we have D1, an algorithm can only deploy H1 here with probability smaller or equal to 1/4. Otherwise, it is unfair. And the same with H2 on the distribution, the second distribution in this case. And next, as a corollary of Pinsker's inequality, for this many rounds, for the order of like at least beta over gamma squared rounds, you cannot distinguish the probability that you play any hypothesis on the two distributions by more than beta. So the probability that you play H1 on D2 is the same as the probability of playing H1 on D1 with a difference of at most beta. So in both of these cases, the takeaway is that the probability that you play either H1 or H2 in both of these cases is at most 1/2 plus beta. So you're going to play with probability close to 1/2 one of these two hypotheses, positive or negative, which are very suboptimal. So for each of these rounds that you have here, you're going to suffer linear regret. And if you set gamma to be t to the minus 1/4, you get that for t to the minus 1/4 fairness, at least the regret has to be at least t to the 2 times, root t to the best fair policy.
Yeah. On the last slide,
Yeah.
was there anything special about having 4 gamma over there? It seems like it could be any arbitrarily large
Oh no, there's nothing. It's nothing special about this. This is just one selection. It doesn't have to be 4 times gamma.
But it seems like you could make it an arbitrarily large number of times gamma, which means that you can't play H1 or H2 with very large probability at all.
So in the formal statement, I don't think it's arbitrarily large. So in the formal statement, you also have, like, we have a high probability statement that also enters the picture. But maybe it's not arbitrarily large, but a constant times gamma. It's what you can
Yeah,
get with.
some arbitrarily large constant times gamma. Which effectively. Like I'm asking on the last slide.
Yeah. Whether it's an arbitrarily large constant.
Can we make that triangle arbitrarily long, or is there something special about 4 there in that picture?
So that this 4 is affecting the ability to play, so you can play with just a probability 1/4, right?
Yeah.
If you make it arbitrarily large, yes, you can make it larger.
Yeah, that'll increase the KL divergence between the.
Yes. But I guess like any constant that you put it, any constant would maybe work, but other than a constant, I don't think the KL divergence would be. Okay, so like two points that before I end my talk is, so 2 open problems that come from the paper is, while we have both false positive and false negative constraints. So if we want to enforce deploying a policy that gives us gamma false positive and gamma false negative at the same time, how do we get that? And this is not so simple. It turns out that we don't really have an efficient or like an efficient way of doing that and achieving low regret, and it has to do with the structure of the hypothesis class. So if you want to optimize over one constraint, you can always use a hypothesis that is predicting according to the protected bit in the other direction, and sort of on average get rid of discrimination without paying a lot of regret. This is something that we don't really know how to do efficiently when we have 2 constraints. Another question is, what happens with other definitions of fairness? So I mentioned it works also for statistical parity, but other definitions, we might think what happens with calibration, for example, or other definitions of fairness. It's not yet clear what are the trade-offs that we can get, but I think it's an interesting question. That's it. Thank you.
Time for questions, if there are any.
Yes.
Is this a common scenario with the one-sided feedback? Is that a common practical scenario?
Yes, so it's a very common practical scenario. So every lending or every hiring scenario or medical trials, for example, only if you administer the treatment you find out if it's a successful or non-successful one. Only people that you lend money to are the ones that you can see if they repay your default.
Try to estimate it by, like what we had in the talk, in the previous talk in the morning. You can try to estimate it by allowing people arbitrarily at the beginning just to.
Yeah, but you cannot do it in every case, though. Like if you talk about medical trials, or if you talk about predictive policing, so yeah, lending.
That it's being done.
Yes, because lending exploration is also the outcome. The outcome that comes from exploring on an individual is a positive outcome because you give a loan. But if you try a new treatment, or like with recidivism, if you just let people randomly go at the beginning, that's very problematic. You can't really.
No, but we know that we do it with accepting students to programs. So in some contexts.
In some contexts, that's perfectly acceptable. In some other contexts, we might want to consider what's at stake.
Did you have a question, Cynthia? I thought I saw you raise your hand. Okay. Great, let's take the rest of the questions.